Then you guys start working on question 4. This week we're going to do question 4, 5, 6, and 7, right, from sheet number 4. Alright, let's start with question 4, guys. Right? Alright, sir. Alright, sir. I know some of you have already done question 4. I'll give you a few minutes. You guys sign this? Alright, let me show you how to do. I mean, any question in mathematics, you can do it in multiple different ways. And the same applies to statistics. So here you have a random sample from a normal distribution with parameters alpha plus beta. Alpha plus beta is the mean, and variance is equal to 1. Now, if you guys remember what we did in the lectures, if you have a random sample, from a normal distribution, then the MLE for the mean parameter is equal to what? I did this question in the lectures, guys. If you have a random sample from a normal distribution, then the MLE for the mean parameter is equal to. Do you guys remember this result? That I did this example in the lectures some time ago. That whenever you have a random sample from a normal distribution, the MLE for the mean parameter, the mean here is alpha plus beta, is equal to the sample mean, which is x bar, right? And similarly, you have another sample. So this implies that alpha hat plus beta hat is equal to x bar, right? Call this equation 1. Now, similarly, you have another random sample from a normal distribution with the mean equal to alpha minus beta and the variance equal to 1. So by the same argument, the MLE for alpha minus beta is equal to the sample mean, which is y bar, which is the same as saying that the MLE for alpha minus the MLE for beta is equal to y bar. Call this equation 2. So you now have two equations and two unknowns. The unknowns are alpha hat and beta hat. So if you add equation 1 and equation 2, guys, you get 2 alpha hat equal to x bar plus y bar, which implies that alpha hat is equal to this, where on the other hand, if you subtract equation 2 from equation 1, you get 2 beta hat is equal to this, which implies that beta hat is equal to x bar minus y bar divided by 2. Guys, is this? So this is one way to do the problem. I mean, there are other ways to do. Is this clear to all of you, or anybody not clear? Huh? You alright, guys, or not? Yes? No? Yeah? We are doing question 4, guys, if you came late. Because if you came late, we are doing question number 4 from sheet number 4, right? Are you okay with this, guys? Yeah? Alright. So this is perhaps the shortest way to do the question. A longer way to do the same question is as follows. Can I take this away, guys? Yeah. All right. So the same question number 4. Right? If you want, another way to do this is to write down the likelihood function for alpha and beta, which will be the product for I from 1 to n of yeah. Yeah, this is the joint likelihood function for alpha and beta. So you see there are two products, because this is for the first sample x1 to xn, and this is for the second sample y1 to yn, right? And the next step is to take the log of the likelihood and then take the partial derivatives with respect to alpha and with respect to beta. And then if you solve these two equations, you will, after a longer process, you will get the same answers. That is, your solutions for alpha will be this, and your solution for beta will be this. So this is a second approach. This is another way to do the same question, guys. But this is, as you can see, it will be a lot longer than the first approach, right? Because here you need to write down the likelihood, simplify it, take the log, take the partial derivatives, set them to 0, and solve for alpha hat and beta hat, which will be a lot longer process of. So the first approach I showed you a minute ago is much simpler to do this question. Is that clear or not? Yeah. All right. Can you now do the next question, guys? Question 5. Question 5. So this is the second approach to do question 4. The first approach I just showed you a minute ago. You guys do question 5, please, now. The question 5 involves the gamma distribution, which is the formula for the density of the gamma is in the lecture notes on page 8. If you look at page 8 of the lecture notes, equation 35, that gives the density of the gamma distribution. You guys okay?
Yeah.
okay. So, we are doing question 5 now. Question 5. Right. Okay. We have a random sample from a gamma distribution with these parameters, but we are told that the parameter r is known. So the value of r is known. So the only parameter that is unknown is the parameter lambda. So this is basically a scalar MLE problem. So it's an MLE problem with just one parameter. So the first thing you need to write down is the likelihood function of lambda, because lambda is the only unknown parameter, right? So if you go to page 8 of the lecture notes, you will see that the density of the gamma distribution is on equation 33.5. All right, this is by equation 35 in the lecture notes, guys. This is what you have. Now, if you simplify this, guys, you get this is the simplified form of the likelihood. Now the next step, I'm sure you guys done this many times already. The next step is to take the log of the likelihood. Yeah, you're right. So this is the log likelihood, guys. And the next step, you guys know, this is the derivative of the log likelihood with respect to the only parameter, which is lambda. So you get nr by lambda minus the sum of xi, I from 1 to n. Set this to 0 and solve for lambda. You get lambda hat equal to this, which is the same as writing that r divided by the sample mean. So this is the solution for this equation. Now remember, in the scalar case, you must show that the solution for this equation is indeed an MLE. To do that, you need to do the second you need to find the second order derivative with respect to lambda, which is this, and which is of course negative all the time. So hence lambda hat equal to this is an ML, is a maximum likelihood estimate, right? Is that clear, guys, so far? Yeah. Now to do the second part of the question is to find the MLE for the function of lambda. This is tau, is a Greek symbol, guys, not to be confused with r. Tau is equal to, is a function of lambda, 2 lambda minus 1 squared. So the MLE for tau is simply the function with lambda replaced by lambda hat. Okay, so it will be 2r. So this will be the MLE for tau, the function of lambda. Okay, guys. So whenever you have a function of a parameter and you know the MLE of that parameter, all you have to do is just replace that parameter by the MLE to find the MLE of the function, right? All right. That's okay. Can we do the next question? By question 6.
Yeah, that's nice.
Oh, you have one.
So, I know somebody gets 1,000 likes, but it doesn't like them because they look on it. That's so sad. I don't know.
Let's do 6, please, now.
Yeah.
It's the same argument as question 4. Because we have a random sample here, right? The MLE for lambda 1 is 1 divided by the sample.
Yeah, no, stop.
Yeah, similarly, the MLE for lambda 1, lambda 2 is the 1 divided by the sample mean of this.
One, y.
1 divided by y bar.
Yeah, one divided by one.
Yeah, is equal to MLE of lambda 1 times MLE of lambda 2.
So if that's the case, that should be
Yeah.
times it by the MLE of 1 and 2.
Yeah, yeah. The MLE is the MLE of the product of the two is equal to 1 divided by
Yes,
y.
1 divided by x bar 1.
Not really. Yeah, slightly like this. Slightly. The MLE of lambda 1 lambda 2 is equal to 1 divided by y bar.
Okay.
Yeah, and then solve this equation and this equation. You guys, okay. All right. Let me. Question 4 is question 6 is kind of similar to question 4. I mean, you can do it in multiple different ways, guys. This is question 6, guys. You have x1, x2 up to xn IID exponential with parameter lambda 1. Now, I think I did one of the questions I did in the lectures, if you guys remember, is the MLE for the exponential distribution. And I'm sure you guys have better memory than I am. You should remember, guys, the lambda parameter, the MLE for the lambda parameter in the example I did was 1 divided by the sample mean. Do you recall that or not? You don't? Oh, you do. So if you recall that, I mean, you can look back in the scan notes, guys. You will see that. So this implies that the MLE for lambda 1 is equal to 1 divided by x bar, the sample mean, right? And then you have another sample y1, y2 up to ym IID with exponential with parameter lambda 1, lambda 2. And by the same argument, guys, this implies that the MLE for the product, MLE for the rate parameter, which is lambda 1, lambda 2, is equal to 1 divided by the sample mean, which is y bar. The same as saying that call this 1, call this 2. Now, if you divide equation 2 by equation 1, guys, we get lambda 2 hat is equal to x bar divided by y bar, and lambda 1 hat is of course equal to 1 divided by x bar. So this is the shorter way to do the question, guys. The alternative approach to do this same question is to write down the full likelihood. Write down the full likelihood function for lambda 1 and lambda 2, and then take the partial derivatives of the log likelihood, and then solve the equations, which you will get the same answers. You will get the same answers as these two. You know what I'm saying, guys, or you don't? The alternative approach is to, so this is question 6 one more time. Question 6. The alternative approach is to write down the joint likelihood of lambda 1, lambda 2, which will be excuse me. Which will be this multiplied by Yeah. So this is the joint likelihood function of lambda 1 and lambda 2, and then you take the log of the likelihood, right, and then you do the partial derivatives with respect to lambda 1 and with respect to lambda 2. Yeah, and then if you solve these two equations, you will get the same answers, that lambda 2 hat is equal to this and lambda 1 hat equal to this. But this approach will be much longer than the first approach, right? Because as you can see, you need to simplify the likelihood, take the log, take the partial derivatives, set them to 0 and solve them. So it is a lot longer approach. Yeah. Is that clear, guys, or not? Questions, guys, please. Yeah. You should get the same answers. Unless you. What I mean, just sub lambda 2 hat. So you got this from equation 2, right? Yeah. So sub it in here, equation 1, and then solve for lambda 1 hat.
Yeah, so I've got it here. Yeah.
But you need to simplify this further. Yeah. Any other questions, guys? Are you guys okay with this? You want to say? And can you do question 7, please, if this is okay? Yes. Guys, either way, you should get the same answer. If you're getting a wrong, different answer, make sure recheck your calculations. Do you understand this?
I don't know, I can't really remember.
is 6, so we don't know when it's but the match user, I feel like it's the best.
That's my problem. Like that's quite
Oh,
like
you're
it.
getting on Slack. It's gone.
I think it will be because I'm bit of time off to go back fresh. Ready to fight. So soon.
I just need to get the right level of it.
Can you guys do question 7, please? If you're okay with question 6, can you do 7, please? Can you guys listen? Can you guys listen, please, for question 7? Right, question 7. Let's try the standard approach first. All right. The standard approach is to write down the log likelihood and simplify it. This is the simplified form of the likelihood. Take the log. This is the log of the likelihood, guys. And then take the derivative of the log likelihood with respect to the parameter, which is delta, which is n. Now this equal to 0 it has no sense at all. It's complete nonsense that n equal to 0, right? So that what this means is that the standard approach does not work. So if it doesn't work, what do you guys do? If the standard approach doesn't work, you try the indicator I'm sure I said this many times, guys. If the standard approach fails, then you try the indicator function approach, right? So you rewrite the likelihood. Now this time you need to put the indicator function that, remember, xi is greater than equal to x is greater than equal to delta. So you must say that every xi is greater than equal to delta. So you write your likelihood as the product of this, right? Making sure that you put in the indicator function, right? So this becomes this. Right, now this is where I'm going to ask you a question, guys. Now I'm going to test your memory. Remember, I gave you three rules for simplifying products of indicator functions. It's in your lecture notes somewhere. Not in the printed version, I mean the scanned lecture notes. Do you guys remember what would this simplify to, guys? Huh? Alright, good, guys, good, really good. So this will simplify to the min of xi greater than or equal to delta. If you guys wonder where this came from, just look in the scan notes, guys. There are 3 rules I gave you to simplify products of indicator functions. So this is using one of the 3 rules, right? Alright, the next thing to do, guys, is to plot. This is where your skills in calculus come in. So I'm going to plot L of delta versus delta. Now suppose this corresponds to the min of xi. Now, how do you think the graph will look like, guys? Now, on this side, guys, delta is greater than the min of xi. So this fails to hold. Therefore, the function will be the function will be 0. The function will be 0 on this side. Yeah. Now on this side, how do you think the function will look like? Increasing. Why? Why is it increasing? Because you have n delta here, right? N delta is an increasing function of delta because n is a positive constant, right? So you have what you have is a increasing function. So the largest point of the graph is over here, right? And the corresponding delta is this, and therefore the MLE for delta is the min of xi. Question done, guys. Is that I did several questions like, you must be familiar with this kind of stuff by now, because I did several questions like this in the class. You have that one. Just one about the lecture yesterday, right? The one on sampling distributions. Please try to prove the properties I did not prove in the lecture yesterday. If you have problems proving them, just please send me an email or come and see me in my office. I'm in my office 11 to 5, Tuesday to Friday. You just drop in. You don't need to make an appointment, guys. Okay? All right, guys. Okay. I'll show you now. Just a minute. This one. Is it this one? Or the first one? Oh. Yeah, this one. Yeah, this one. Not this one. Oh, the first approach. Is it question 4 or question? Which question is it? Is it this one? Yeah. This one. Okay. Hi. Yeah. You understand? Because if you look at the lecture notes, the scan lecture note, you will see that when you have a random sample from a normal distribution, the MLE for the mean parameter is the sample mean. Yeah. You remember that? And similarly, for the exponential distribution, when you have a random sample from an exponential distribution, the MLE for the lambda parameter is 1 divided by the sample mean. You just look in the scan notes for the lectures. I told those in the lecture. Yeah. Do you have any questions? Yeah. Yeah. The mean, yeah, the mean parameter. This is the mean, right? When you have like, you have a chalk. Just a minute, I don't have a chalk. No. So yeah. But when you have like x1, x2 to xn, if it comes from a normal distribution with these parameters, then mu hat is equal to x bar. Yeah, this is the property I used in question 4. And similarly, you should have x1, x2 to xn from an exponential distribution with parameter lambda, then the MLE for lambda is 1 divided by x bar. This is what I used in question 6. Is that?
Now about the
Sigma, we don't need sigma here because sigma was 1. In this question, the sigma was equal to 1. Sigma is equal to 1. Yeah. And any other questions?
No.
Just feel free to come and see me, man.
okay.
I'll help you. Yeah.
Any for that?
Yeah, man. Yeah. You can come and see me in my office anytime. You don't need to make an appointment. Okay.
In office hour.
Anytime from anytime from 11 to 5.
Oh.
Anytime. Yeah.
Okay.
Yeah. My office is 2.223. It's in the second floor of this building.
Basically, I have the written exam, so if I have time, I will come.
Okay.